Hello, my name is Pedro Capitão, and I'm going to talk about private constrained pseudorandom functions with succinct keys. My master thesis project is about private constrained pseudorandom functions. In this presentation, I'm going to introduce some background about constrained pseudorandom functions and show some constructions that are based on the learning with errors problem. In the end, I'm going to talk about the problem that I'm addressing in my thesis and explain the approach that I'm using to solve it. Pseudorandom functions are deterministic and efficiently computable functions that are indistinguishable from random functions. They are basic cryptographic objects that can be built just from one-way functions, and they have many applications, particularly as building blocks in more complex protocols. In a constrained pseudorandom function, the owner can generate constrained keys, each corresponding to a constraint over the input space, and one of these keys allows its user to compute the value of the PRF only at the points that satisfy that constraint. In a private constrained PRF, we have a stronger security requirement, which is that the constrained keys must not reveal information about the corresponding constraint. They have applications including watermarking PRFs and private constrained message authentication codes. We can define a pseudorandom function as a pair of algorithms. The key generation algorithm receives the security parameter lambda and is a probabilistic algorithm which generates a key. And then the evaluation algorithm, which is deterministic and has on input a key and a value x, outputs the value of the function y. And the security of this function is the pseudo-randomness property, which can be formally defined like this. If we call x lambda the input space and y lambda the output space of the evaluation algorithm when the key is generated with parameter lambda, and we denote by f lambda the set of all functions from x to y, then for any probabilistic polynomial time algorithm A, we consider these two experiments. In the first, A has oracle access to the evaluation algorithm with the key k that is generated according to the key generation algorithm. And in the second experience, A has oracle access to a function f, which is uniformly sampled from the set of all functions. And so we require that the difference between these two probabilities of A outputting 1 in each of the experiments is a negligible function of lambda. So this captures the property that the adversary cannot distinguish between the points where the actual function was evaluated and the values of a randomly chosen function. The learning with errors problem is the most commonly used hardness assumption in lattice cryptography. So the decisional learning with errors problem is to distinguish between these two distributions, where A is a randomly sampled matrix of integers modulo q, S and U are also uniformly sampled vectors, and E is a small error vector, which is usually sampled from a discrete Gaussian distribution. And so what we are saying here is that given the matrix A, it is hard to distinguish between this vector AS plus E and a uniformly random vector. there exist classical and quantum reductions from LWE to problems on lattices for which there aren't any known efficient algorithms, such as the approximate shortest vector problem. And because of these protocols whose security is based on the hardness of learning with errors are conjectured to be secure against both classical and quantum attacks. As a first example, let us examine this pseudorandom function from the learning with errors, which has as public parameters these two matrices, A0 and A1. The key is a vector S randomly sampled from ZQM. And the evaluation algorithm, given a key S and a binary string X, outputs this expression, where we compute the product of the matrices A0 and A1 according to the bits of X. This product is modulo Q. And then we multiply by S. And finally, we apply this rounding operation, which goes from ZQ to ZP, where P is a significantly smaller modulus. And it is just multiplying by P, dividing by Q, and then rounding to the nearest integer. So notice the similarity between this expression and learning with errors. In a LWE sample, we had a matrix A multiplied by S plus some small error E. Here, since the output of the pseudorandom function is deterministic, this evaluation algorithm must be deterministic, we cannot have that random error. And so we have this rounding operation performing that role. Observe that when we have two values that are very close and we round them, then we obtain the same result, at least with very high probability. Now I'm going to introduce constrained pseudorandom functions alongside their encryption analog, which is attribute-based encryption. So let us start with attribute-based encryption, which is composed of these four algorithms. The setup algorithm generates a public key and a secret key. The encryption algorithm uses the public key because we are in the public key setting, but it also exists in the symmetric key setting, and an attribute X and a message mu. So here encryption is always done with attributes which can be freely chosen. Then we have the constraint algorithm, which given a constraint F outputs a constraint key, and the decryption algorithm. And the property which is fundamental here is that a constrained key allows us to decrypt a ciphertext that was encrypted with attribute X if and only if X satisfies the constraint F, which we denote by f of X equals 0. This is contrary to the more usual convention of 0 being false and 1 being true, but it is more practical in the technical parts. On the other hand, a constrained PRF is composed of these four algorithms where the key generation and evaluation are the same as in a regular PRF. Then we have the constraint algorithm, which generates constrained keys, and the constraint evaluation algorithm, which calculates the output of the PRF using a constrained key instead of the master key. And the property that this must satisfy is that a constrained key allows the user to obtain the correct value of the PRF at a point X if and only if f of X is 0. These constraints that I'm talking about are circuits that output either 0 or 1, and they are represented by binary strings. And we say that an attribute-based encryption or constraint PRF has succinct keys if the size of the constraint keys is independent of the size of the description of the circuit. Before moving on to the next example, I'm going to introduce this technique, which is homomorphic evaluation of circuits on matrices, also sometimes called lattice evolution algorithms. And it is composed of these two algorithms, eval-P and eval-C. The first takes as input a circuit F and matrices B1 to BL and outputs a matrix. And the second takes a function F, an input X, these matrices B and these vectors C, and outputs a vector. And they have the essential property that if the CIs are of this form, that is, they are LWE samples with this matrix here that encodes the BIs and the XIs, then the output C of F and X is of the same form, where here we have the matrix BF and here F of X. In these expressions, G is this block diagonal matrix where each block has these powers of 2, and it is called the Gadget matrix. And the authors who introduced the technique in this form, they proposed also an attribute-based encryption with succinct keys using this tool. Okay, the next example is a constrained pseudorandom function based on learning with errors. It has as public parameters matrices A0, A1, and B1 to BL, and the secret key is a vector S. In the evaluation algorithm, we consider this universal circuit U, which receives as input the description of a function F and a binary string X, and outputs F of X. Okay, here we are using again these algorithms eval-P and eval-C that we just saw, but now the inputs X are binary strings instead of vectors in modulo Q. So we compute this matrix BU, which is eval-P of the circuit U on these matrices that we see here, and the output is S multiplied by BU, and then we apply the rounding operation. A constraint key for a function, a circuit F, is composed of these vectors A0 and A1 of this form, and these BIs where we have one for each bit Fi of the description of F. Finally, the constrained evaluation algorithm does the following. It computes eval-C of the circuit U on input F and X over these matrices and vectors. So recall that U receives two inputs, a function and a string. And here the matrices B and vectors B correspond to F, and the A's correspond to X. And the output is this vector rounded to ZP. The correctness of this scheme follows directly from the properties of eval-P and eval-C, which give us this equation. And so when the constraint is satisfied, we have that F of X equals 0. And so this term disappears, and we are left with S times BU plus some small error. And so when we apply the rounding operation, the effect of that error disappears. And so when the evaluation is authorized, the regular evaluation and the constrained evaluation algorithms output the same value. On the other hand, and this is the security requirement of pseudo-randomness under constraining, if an adversary has arbitrarily many keys that are unauthorized, then then he does not gain any information about the values of the function on unauthorized points. That is, they remain indistinguishable from random values. I want to note that I'm presenting here a simplified version of this construction. In the original constraint PRF, there are a couple more variables which are important in the security proof. This scheme is selectively secure. This is a weaker notion than full or adaptive security, in which in the security game, the adversary has to choose a constraint F at the beginning of the game before being able to make any queries. The authors of this constraint PRF that I just presented also proposed a variant of their scheme in which the keys are succinct. That is, they are independent, their size is independent of the size of the circuits. And to do this, they use within their scheme an attribute-based encryption which has succinct keys. And so recall that just now we had as part of our constraint key a vector bi for each bit I of the description of the constraint f. So the main change here is that now we compute these bi's right at the beginning for all possible values of the bits of the constraint. So we compute b of I beta for beta equals 0 and beta equals 1. And then we encrypt each of these vectors using attribute-based encryption with the attribute I and beta. And we publish them together with the rest of the public parameters. The evaluation algorithm is exactly the same. And then when we want to give a constraint key for a function f, we consider this constraint phi of f, which accepts I and beta if and only if fi equals beta. And so we give a constraint ABE key for this constraint phi of f together with the other vectors a0 and a1. And now for the constraint evaluation, we do the following. We, using our constraint key for the ABE system, we decrypt these ciphertexts, the ones that our key allows us, which are the ones such that fi equals beta. And so we obtain the vectors bi, which were in the previous scheme given directly as the constraint key. And so we can compute, as usual, the value y of the PRF. Before we talk about the last construction, I'm just going to introduce the notion of fully homomorphic encryption, which is an encryption scheme with an additional algorithm for evaluation, which allows computation over encrypted data. It consists of 4 algorithms, where the first 3 are just for setup, encryption, and decryption are just a basic symmetric key encryption scheme. And the last one for evaluation receives as input a function f and the ciphertext c and outputs another ciphertext. And it has the property that if c is an encryption of a message mu and c prime is the evaluation of f on c, then when we decrypt c prime, we obtain f of mu. This is a powerful cryptographic primitive, which can also be built from the learning with errors hardness assumption. Now let's look at this private constraint pseudorandom function, which uses a particular fully homomorphic encryption scheme, this GSW scheme. And recall here that private means that the constraints are hidden. The constraint key does not reveal its corresponding constraint. Our public parameters are these matrices, and the secret key is a vector S. To evaluate the function at an input point x, we let u of x be the circuit that receives the description of a function f and outputs f of x. And we consider this other circuit ux hat, which does the following. It takes as input a fully homomorphic encryption psi of a function f. Then it computes psi x, which is the homomorphic evaluation of the circuit ux on psi, and it finally outputs psi x bar, which is the matrix psi x with the last row removed. This is just because in this particular fully homomorphic encryption scheme, the last row plays a special role. And now we are going to use these algorithms eval f and in the next slide eval fx, which are slightly different from the lattice algorithms eval c and eval p that we saw before, but they serve the same purpose. And so we compute age, which is the evaluation of this circuit on these matrices B1 to BL, and then we multiply it by this block matrix composed of the matrices B1 to BL. And finally, we multiply it by S and apply the rounding operation, and that is our PRF output. When we want to give a constrained key for a constraint F, we first compute psi as the fully homomorphic encryption of F, using S as the secret key. And then we compute these vectors Cj of this form, where we have one for each bit psi j of the binary representation of psi. And our constraint key is psi and the vectors Cj. Finally, the constrained evaluation algorithm computes this matrix age of u and psi, which is eval fx of this circuit on input psi over these matrices. Then we compute again psi of x, which is the homomorphic evaluation of ux on psi. We multiply it by these vectors C1 to CL, and we sum the last row of psi x. Finally, we output the result after applying the rounding operation. So by a similar analysis than what we did earlier, and by the properties of the fully homomorphic encryption scheme, this scheme is also correct. That is, when f of x equals 0, we get the same output through the evaluation and through the constrained evaluation algorithms. This scheme is also selectively secure, and it is not collusion secure, not collusion resistant, meaning that it is secure against an adversary that has only one constraint key, but if the adversary has access to more than one constraint key, he can potentially break the system. The main objective of my master's thesis is to build a private constraint pseudorandom function scheme with succinct keys based on this private constraint PRF that I just presented. And so my idea to do this was to try to apply the same technique that I showed you earlier, where we had a constrained pseudorandom function, and then we used attribute-based encryption to encrypt right at the start the constraint keys, and so making the constraint keys succinct in the end. So let's see what happens if we try to apply the same technique here. Recall that our constraint keys here are psi, which is composed of the fully homomorphic encryption of each bit fi of the description of f, and this vector Cj, where we have 1 for each bit psi j of the binary decomposition of psi. So notice that these are both of polynomial size on the length of the description of f, and so they are not succinct. And so we use the previous technique, and we include in the public parameters ABE encryptions of psi of I and beta, where we encrypt the bit beta with fully homomorphic encryption, and then we encrypt that with ABE with the attribute I and beta. And the same for the C's. We encrypt C of J and beta with attribute J and beta. And then our constraint key would consist of the ABE constraint keys for these two constraints. Phi of f, which accepts I and beta if and only if fi equals beta, and lambda, which accepts j and beta if and only if psi j equals beta. The problem with this approach is that now the attribute-based encryption key for this function phi f reveals the constraint phi f, which in turn reveals f. And so we want to achieve private constraint PRFs, constraint hiding PRFs. And so this just does not work, and so we need something more. So our approach was, instead of using this attribute-based encryption, we apply the exact same technique, but with something stronger, which is function hiding predicate encryption. Predicate encryption is itself a stronger, more secure form of attribute-based encryption, where the ciphertexts hide not only the message, but also the attribute. And in function hiding predicate encryption, the constraint keys also hide their respective constraints. And this cryptographic object exists based on learning with errors in the symmetric key setting, which is all that we need. But this raises another issue, which is that this function hiding predicate encryption does not have succinct keys. We don't know of any construction that does. It may very well be impossible, in fact. However, we can find a way to get around this problem, which is to observe that the constraint key has two parts. The first part is a constraint key for an underlying predicate encryption, which is not function hiding, just a regular predicate encryption scheme. And these can be succinct, independent of the size of f. So we send that as the constraint key. And then the second part is a symmetric key encryption of f, which obviously depends on the size of f. But we can safely add it to the public parameters because it gives no information to a possible attacker unless they have either the master secret key or the respective constraint key associated to f. To put it another way, with this approach, our constraint key has a private part, which is succinct, and a public part, which is not, but it doesn't have to be because we just put it together with the rest of the public parameters. Yeah, so this is the point where I am in my master thesis project. There is still a lot to do. We have to prove that this approach indeed works, namely do the proofs of correctness and pseudo-randomness and constraint hiding, of which constraint hiding is by far the hardest, but we think that it is going to work out. There is still work to do, and we do not have, I don't have any results to show at the moment, but I hope you liked this presentation, and thank you very much.